So what happens when you have a liquid with high viscosity? Where do you put it? Should we put it on the shell side or should we put it on the tube side? Okay. So as part of our studies, all of us must have come across some dimensionless numbers like Reynolds number, Grashof number, Prandtl number, Nusselt number and all. So one dimensionless number which has to do with most heat transfer equations is Reynolds number. Reynolds number is nothing but the ratio of inertial forces to viscous forces in the fluid. Well, if you go by the formula, Reynolds number is a product of density multiplied by diameter multiplied by the velocity of the fluid divided by the viscosity of the fluid. So when we have a high viscous fluid, it means that the viscosity of the fluid is high. So which in turn means that the Reynolds number is going to be low. A low Reynolds number means that your heat transfer is also going to be low for that fluid. So how do we improve the Reynolds number and how do we improve the heat transfer? That is what we need to see when we are deciding to place a high viscous fluid, on which side we need to place it. So what are the advantages or disadvantages if you place a high viscous fluid on the tube side? So on the tube side, you can improve the velocity only by increasing the number of passes on the tube side. That is how you can improve the velocity. Keeping your diameter constant, if you increase the passes, your velocity will increase. But this velocity increase will also be coupled along with a reduction in the number of tubes you can accommodate within the shell. This is because you have some pass partition lane clearances. So the number of tubes would reduce within that shell. So that leads to a reduction in heat transfer area also. So for that, to compensate for that, we will again increase the shell diameter or increase the tube length. In addition to all these, pass partition lane clearances also lead to leakage streams in the fluid. So you have different streams going in, like what we call as a cross flow stream, and then the leakage stream between the shell and the shell inside and the bundle outside, or between the baffle out OD and the shell ID. So we have leakage streams and effective streams. So the leakage streams would also increase because of the pass partition lane clearances now. What happens if we place the fluid with high viscosity on the shell side? On the shell side, you can improve the velocity and turbulence by changing the baffle cut or the baffle spacing. And this will lead to an increase in the Reynolds number and hence an increase in the shell side heat transfer coefficient. Additionally, when we have baffles, we have a cross flow on the heat exchanger, and cross flow heat transfer coefficients are generally much higher than heat transfer within straight tubes, because the amount of turbulence which we create in cross flow is more compared to flow through straight tubes. So considering these factors, the recommendation is generally to locate the high viscous fluid on the shell side of the heat exchanger. Let's now see the next one, where you have liquid with suspended solids or slurry. So what happens when you place such a fluid on the shell side? On the shell side, because of the presence of baffles, there are chances of solids accumulating at the bottom of the shell, as well as erosion of the baffle plate due to constant impact with the solid particles. And in case of fixed tube sheet exchangers with expansion bellows to take care of differential thermal expansion, there's a chance of accumulation of solids in the bellows also, within the bellows. Now, if we have this on the tube side, you have various ways in which you can control it. There's no accumulation inside the tubes if you maintain a reasonably good velocity of the fluid. Then chances of solid accumulation is there in the channel boxes, but it's much easier to clean. Then you can also use higher tube diameters so that chances of accumulation is reduced. Chances of clogging of the tubes is reduced. So effectively, it is better to place the fluid with suspended solids inside the tubes. Okay. Now what do we do with a fluid with a high flow rate? So again, as with viscosity, again, it's the Reynolds number which will influence our decision on where to place a fluid with a high velocity. Once we are saying a fluid with a high flow rate, it generally also means that we have a reasonably good velocity for that fluid. So your Reynolds number would already be a bit higher. So what would you do in such a case? Where would you locate it? So if you put it on the shell side, what you are again playing around with is the baffle cut and the baffles to improve the turbulence and increase the shell side heat transfer coefficient. Now, compared to this, what happens if you put that fluid on the tube side? As it is, you already have a good velocity and a Reynolds number. So if you further want to increase the velocity and improve the Reynolds number and heat transfer, you are left with no other option but to increase the number of passes again. But increasing the number of passes will increase the velocity, but substantially increase the pressure drop also significantly. So we should check whether that higher pressure drop is permitted or not permitted for the client, because every client would be, once they specify a allowable pressure drop to you, it's generally recommended that we stick to that pressure drop. We do not exceed it, because finally the client has done some pump head calculations based on some allowances for pressure drop and line losses which they have considered. So increasing the tube passes also leads to a reduction in the number of tubes, and again to leakages because of pass partition lane clearances. So due to all these factors, it's a recommendation that we should have the high flow fluid on the shell side again. Now, what do we do when you have a fluid with a high operating pressure and a high design pressure? Now, here it's got to do with a little bit of mechanical design. This is the formula for thickness of any circular component as per ASME Section 8 Division 1. Whether it is for a shell or a tube, P is the pressure, R is the inside radius, E is the joint efficiency, S is the allowable stress value for that material, and again P is the pressure. So if you see here, for a given material and temperature conditions, stress value is fixed from the code. Joint efficiency for based on your quality NDT, you can decide the joint efficiency that's fixed. Your pressure is fixed. It's only the radius. So thickness is proportional to radius. The higher your radius or diameter, the higher your required thickness. So based on that logic, if you place the fluid on the shell side, the fluid with the high operating pressure on the shell side, the shell is much bigger in diameter compared to the tubes. So effectively, you would end up having a very thick shell, which is again a cost impact. Compared to this, placing it on the tube side, the tubes being much smaller in diameter, your thickness is less, and moreover, the minimum required thicknesses given by the design codes are generally adequate up to a fairly good amount of pressure. So you are not increasing any thickness of the tubes beyond what is recommended by the minimum recommended by the design codes. So there's no cost impact because of this generally. So the recommendation would be to place the high design pressure fluid on the tube side so that you save on the overall cost of the unit. Then fluids with low allowable pressure drop or fluids in vacuum service. So if you place this fluid on the shell side, then the pressure drop can be controlled on the shell side. You always control the pressure drop only by varying the baffle designs, basically, or by selecting a different TEMA type of exchanger. Like if you select a X type shell or a split flow shell, then you can control the pressure drop on the shell side. On the tube side, your pressure drop control is only based on the tube diameter or the number of passes. So the recommendation is always to have the low pressure fluid on the shell side of the unit. Now, fluids with a large temperature difference, that is temperature difference between in and out, if it is more, then if you place such a fluid on the shell side, it's better able to handle the thermal expansion and differential thermal expansion in a majority of the heat exchangers. What happens is the as a crude estimate, the mean metal temperatures are not are much closer when you have the hot fluid on the shell side, when you have the fluid with a larger temperature difference on the shell side compared to when you have it on a tube side. Additionally, if you have the temperature, the fluid with the large temperature difference on the tube side, you are exposing the tube sheet to a wider temperature profile. And this can lead to distortion in the tube sheet, which is a situation which we would like to avoid because it can lead to leakages at the tube to tube sheet joint. So the recommendation is to place the fluid with a larger temperature difference always on the shell side of the unit. Now, fluids with high corrosion tendency. So what does the high corrosion tendency lead to? It leads us to use special material for that handling that fluid. Now, when you place such a fluid on the shell side, it makes it mandatory for us to, because the shell side fluid is all parts of the heat exchanger, the shell, the tubes on the outside surface, the baffles, as well as the tube sheets. All of these are exposed to the shell side fluid. So when you have a fluid with high corrosion tendency and which calls for special or exotic materials to be used, if you have it on the shell side, all these components should be made from that exotic material. So that leads to a cost impact. Now, when you place it on the tube side, now it's only on the inside of the tubes and the tube sheet and channel side, which need to be of the exotic material. In many cases, in places where we use exotic materials, it is general practice many times that we use for the channel side, for the channels, we use a cheaper material and plan for frequent replacement as and when it is required, so that your initial expenditure is not more. In this case, you only need to make the tubes and the tube sheet from the exotic material. So it's advisable to place the corrosion tendency fluid on the tube side. Now, fluids with high fouling factors. What is fouling? It's nothing but the deposition or accumulation of unwanted material like scale, insoluble salts on the internal and external surfaces of the heat exchanger. If the fouling fluid is on the shell side, it would be fouling on the shell inside as well as on the outside surface of the tubes. If the fouling fluid is on the tube side, it would be fouling the inside surface of the tubes. In either case, fouling will lead to a reduction in the heat transfer coefficient, and in some cases to an increase in the pressure drops also, because if the fouling is extensive, it forms a layer. Once a layer is formed, it reduces the cross section for flow, and this leads to an increase in the pressure drop on that side. So what do we do? Where do we allocate the fluid with the high fouling factors? If it's on the shell side, cleaning is difficult in many cases. Mechanical cleaning, and you would only have to do chemical cleaning to remove the fouling layer. If it's on the tube side, it's easier to do a mechanical cleaning. So the recommendation would be to place the fluid with the high fouling on the tube side of the unit. Now, in some cases, we have fluids which have a requirement to maintain a certain velocity within a certain range, a minimum and a maximum velocity. A typical example for such fluids would be liquids having ammonia salts, where the recommendation is that we should maintain a maximum velocity of 6 meters and a minimum velocity of 3 meters. Now, this velocity criteria has to be met even in cases of turn down conditions. And this is essential to avoid deposition of salts. Unless you maintain these minimum velocities, the unit will be prone to deposition of salts, and that would affect your heat transfer as well as pressure drop values. So in such cases, if you have that fluid on the shell side, again, it becomes first is it becomes difficult to achieve such velocities on the shell side. Shell side velocities are generally much lower than velocities on the tube side. So it is not possible to meet such high velocities on the shell side, and at low velocities, you are prone to accumulation of the salts on the heat transfer surfaces. And if you have it on the tube side, you have the number of passes which you can manipulate in your design and increase the velocity to meet your constraints for that service. So the recommendation would be to place such a fluid on the tube side of the unit. Now, this is just a summary of what we discussed for all the various conditions. If you have a high flow rate on the shell side allocation for a fluid would be preferred when you have a high flow rate or a higher viscosity or fluid with a large temperature difference or fluids with low pressure services or low pressure drop or low pressure services. And on the tube side, you would prefer to allocate the fluid when when it has a high operating or design pressure, when it is a high fouling fluid or corrosive fluid or slurries or fluids where you need to maintain certain velocities. So this is a brief summary of what we saw so far.